Okay, here's a demonstration of the various approximations. Let me start with lower sum. Now, lower sum means that, first of all, I chose the function y equals to 2 plus sine x, which varies like this. And I chose the interval to be from -1 to 6. And I'm choosing 8 intervals. I could increase the number of intervals, just like this one. So right now I have 10 intervals. Okay. Now let me first explain what a lower sum is. Lower sum means for each building site, you look at the function value and use the lowest point to build your rectangle. Now, if you do such a thing, then you will always be underestimating, right? See, we really want to know the area under the curve, whose exact value is given here, 13.58. But we're using the lower sum, so it is less. In our case, it's 12.02. Nonetheless, if you increase the rectangles, you'll see that you get better and better approximations. So here's what happens if we use 20 rectangles, and that's 12.79, which is still bad, but it's better than before, right? Now, this app doesn't let me go beyond this, but if we went beyond, say, in 1,000 or 1 million, you'll get a pretty good result, even if it's lower sum. Okay. Now, what do we do if we get the upper sum? Well, upper sum is the opposite. So what you do is, for each interval, you use the higher value. Now, I notice that this app is slightly wrong. So for example, this picture is wrong because the highest point on the interval from 1 to 2 is somewhere here. So it should be reaching up till 3. So it's not correct. But you get the point, right? All right, now let's try the left sum. What's happening here? How is the rectangles constructed in this case?
On half of them, it's covering over, and half of it it's
Okay,
lower,
that's one observation. Yes?
It's only under on the left side and upper on the right side.
Okay. Yeah, that, yes.
The graphed line intersects with the rectangles at the upper left corner.
That's actually the one that I wanted. Okay, so if you look at the pattern, it's always the case that every rectangle that you see, the top left is located exactly on the graph. Do you agree? It's exactly on the graph, the top left. Is that good? All right. On the other hand, if you're using the right sum, this time the top right corner will be on the graph. You see that? And that's what it means to be left sum and right sum, because you're using the right endpoint to build the height of the building. Right? You're raising up buildings at every construction sites, and you're using the right side of the value of the function to build the rectangle. And the result will be that the top right corner will be touching the graph. Okay, what about the middle? What can you say about this one?
It's the exact same.
Yeah, but say it. The same concept. How do you explain midpoint rule in terms of a graph?
It's the midpoint, or the x1 star, we could say.
Yeah, but say midpoint. Okay, so it's the midpoint of the top that touches the graph, right? Yeah, the graph is passing through the midpoint of the top of the rectangles that you build. So that's midpoint. Okay, now let's move on to trapezoidal. What's happening in this one? What is trapezoidal?
So both corners are touching the tangent.
They are. And actually, that's a good way to explain it. So you have, now instead of the boring rectangular buildings, you're trying to build these fancier roofs where it's slanted in one direction, right? And those are called trapezoids because these two sides are parallel. Okay? You have one side parallel, a pair of sides that are parallel. That means it's a trapezoid. And you can see that both sides of the top are touching the graph. To put it another way is that you can also say that you're trying to approximate the graph by piecewise line functions or piecewise linear functions, right? You're using piecewise straight lines to approximate the graph and then calculating the area under it. That's trapezoid. That's what's happening in the trapezoid. On the other hand, if you use Simpsons, what's happening?
It's really close.
It's really hard to say. Let's see, if I use only 6 intervals, what's happening?
It's staying on the line of the graph. It's just
the
covering.
graph and your approximation seems very similar, right? Why? Why are they so similar?
It's accurate.
Did you tell us that Simpsons is like using parabolas?
Yes, Simpsons is using parabola. So what you're doing is you're choosing the first 3 points and building a parabola passing through those 3 points. And actually, look at the middle one. So if you look at the middle one, you're using the 3 points to build this parabola going down. And you see that although their concavity is same, they're both concave down, right? Yeah. The original graph and the parabola that you're building are both concave down, but they're slightly different, right? You can see that they're slightly different. But nonetheless, you can see that of all these different schemes, the Simpsons will do the best job in approximating, right? And in fact, if you try to use 20 as your n and you use Simpsons, then the Riemann sum is almost same as the exact integral. The only difference is the last digit. So that's how good Simpsons is. Okay? So when you try to find the value of an integral using approximation schemes for engineering purposes, we always use the Simpsons. That's the best. Any questions?